In this question, we're going to look at the electric field that results from two long, thin glass rods that have been uniformly charged. Gives a value for that overall charge on each as 10 nanocoulombs. And they're placed side by side, a certain distance apart, which is 4 centimeters. So it asks what the electric field is 3 centimeters to the right of the rod on the left along the line connecting the midpoints of the two rods. Okay, so I've drawn this out. These questions are really important to get the geometry right. So we have two rods, same length, 10 centimeters, and they're 4 centimeters apart. The point of interest I've drawn in the red X here. Notice that it is 3 centimeters from the left and thus 1 centimeter from the right. Okay. So the overall electric field is going to be the sum of the electric fields created by both rods. And the other thing we already know is an equation for the electric field caused by a charged rod along this midpoint line. And that can be derived considering the symmetry of both sides of the rod. So we know that the electric field of this rod, and I'll say rod, but we mean the midpoint line, is KQ all over R square root R squared plus L over 2 squared. Okay, so that's what we're going to apply. And we're going to apply it twice, once for each rod. We just got to make sure we use the right values. Okay, so EL, so the electric field at that point created by the left rod at 3 centimeters from the left. Well, that's going to be EL is equal to, we know Coulomb's constant, 9 times 10 to the 9 newtons per meter squared per Coulomb squared. And then our charge is 10 nanocoulombs. Just going to make a little note down here that the Q on both QL is equal to QR is equal to Q is equal to 10 nanocoulombs. Just to make that really clear and to keep that handy as a reference. Okay, so 10 times nanocoulombs is a factor of negative 9 coulombs. All right, and this is all over. Ooh, we'll zoom in here. Try and draw this nice and clearly. It's 3 centimeters. So 0.030 meters. Okay. And then we've got in our square root, got a 0.030 meters squared plus L is 10 centimeters. So 0.10 meters over 2 squared. All right. So altogether, we have an electric field at that point that's equal to 5.14 times 10 to the 4 newtons per coulomb. The electric field is a vector. We often talk about the magnitude, but here, since we're going to add a couple together, we need to think about the direction. In this case, it's to the right. Let's back up a moment and take a look at the diagram again. Here's the diagram of the situation. And I'm going to draw not at the midpoint because things are getting a little crowded. But what's going on there is we have a point, and from the left we have an electric field that's going to be directed to the right. Okay. So from the right, we're going to have an electric field that is directed to the left. So not automatically making it an arrow the way I want it. Okay. So this is the electric field that is being caused by the rod on the right, and this is the electric field being caused by the rod on the left. Now, the electric field is dropping off with distance away, and the point here is much closer to the rod on the right, and so the net field we expect will be towards the left. So that's going to be what we expect to see here. Now I could, for the purposes of the math, I could, as we often do, define directions. Say, well, this will be my positive y-axis, and this will be a positive x-axis, and then we can put the values in terms of that and add them together, and we'll get a net result. In this case, there's only two things going on that may or may not be helpful. It's kind of up to you, but that's what we are going to do. So we've already calculated EL. Let's calculate ER and get the net result there. Okay. All right, so the electric field caused by the right-hand rod, so that's going to be 1 centimeter from the right. And since all of this is the same, I'm just going to copy this, and we're going to modify what we need to modify. So the nice thing about these superposition rules is kind of you do it a few times. Okay. So we're now talking about the right, and on the right we have the same charge, the same Coulomb constant, but we're going to have a different distance, and that's going to be 1 centimeter instead of 3. And so now the result, and really we're dealing with the magnitude is going to be 1.76 times 10 to the 5 newtons per coulomb, and that direction is going to be to the left. Okay, and so now we want to add these two together to get the overall electric field. So the electric field is equal to, EL plus ER, and so now, I mean, we could remember they're in opposite directions, but let's just go with the pluses and minuses just for the purposes of adding. I've arbitrarily decided that by convention to the right will be positive, so that means that EL is positive, so that's 5.14 times 10 to the 4 newtons per coulomb minus ER. I mean, it's add, but this was negative, so 76 times 10 to the 5 newtons per coulomb, and this is going to be, hold on a moment, so 5.14 to the 4 subtract 1.76 going to be a negative about 1 point, let's call it 1.3 times 10 to the 5 newtons per coulomb. But you know what? I'm going to rewrite this as saying the electric field, that was a terrible, terrible arrow. Still, I guess I can do better. Okay, so the electric field is going to be, I can also just call this 1.3 times 10 to the 5 newtons per coulomb to the left. Okay? In the context of the question, which is kind of left and right, I think that that's a reasonable way to express the answer. But you got to be a little careful when doing that addition of the electric fields to ensure that you're keeping track of the fact that they're in opposite directions. And so the common mistake would be to just add the magnitudes together, and that's not the case. Okay, so that's it.